Good afternoon, everyone, and welcome to our Fall 2021 iSEE Congress on Circular Food Systems. I'm Luis Rodriguez, the Associate Director of iSEE, the Institute for Sustainability, Energy, and the Environment here at the University of Illinois. Our institute was formed in December of 2013 with a threefold mission of funding and shepherding interdisciplinary research projects that have immediate and lasting impacts on solving global grand challenges related to sustainability, energy, and the environment. Leading efforts to make the U of I campus a leading model of sustainability, energy efficiency, and environmental friendliness. And educating and preparing students to be leaders in these fields when they leave our campus. These congresses fulfill two of these missions, discussing the current cutting edge research and providing an educational opportunities for students. This iSEE Congress is our 8th, and it is hosted in a series of 1-hour discussions about a major challenge for food and agriculture in the coming decades. How do we provide a safe, secure, an increased supply of food, feed, and fuel to an ever-increasing human population while using practices that are ecologically sustainable and adaptable for climate change? Today, I want to let you know we have a Zoom webinar that allows you to post questions to a Q&A field. Notice that there's 2 of these, a chat plus a Q&A. And we'll definitely be taking some time at the end with our speakers to address as many of these questions as we possibly can. So I encourage you to visit that Q&A. Today, we'll discuss how the negative economic and environmental effects of agricultural waste can be mitigated with some cutting-edge processes and technologies. To get us started, I'd like to introduce to you today's moderator, my colleague, Ximing Cai, who also works with iSEE. Ximing is the Lovell Endowed Professor of Civil and Environmental Engineering and iSEE's Associate Director for Campus Sustainability. Ximing?
Thanks, Luis. Welcome everyone to this session of iSEE Congress. The topic today is turning agricultural waste into useful products. I'm excited to introduce our 2 speakers today. First, I would like to introduce Dr. Thomas Trabold. Dr. Trabold is a research professor for the Golisano Institute for Sustainability at the Rochester Institute of Technology. So he is a former department head in the Golisano Institute for Sustainability with primary research focus in the development of alternative energy technologies, including fuel cells, biofuels, and processes for valorizing organic waste materials. Dr. Trabold has more than 20 years of experience in industry research and development at General Electric, Xerox, and General Motors. So in his later position, he was a professional technical fellow and a laboratory group manager with responsibility for engineering research activities in the US and Germany. At RIT, his current research efforts are in thermochemical conversion of organic waste to produce carbonation biochar, and in using biomass derived hydrogen in high temperature PEM fuel cell systems. Dr. Trabold has a strong record of accomplishments in sustainable energy and materials research, with more than 130 technical publications and over 55 US and international patents. Dr. Trabold, so please share with your screen and begin your talk when ready.
All right, thank you, Dr. Cai. I appreciate that nice introduction. Good afternoon, everyone, and thank you for inviting me to participate in this very interesting and innovative program that you have at the University of Illinois. The topic of my talk this afternoon is innovative products using biochar derived from agricultural waste resources. The work I'll cover today is part of a larger effort that has been going on since about 2010 to valorize all types of biomass waste with a particular interest in food waste. We started this work, as I said, back in 2010, due to some of the initiatives in New York State focused on minimizing food waste ending up in landfills. So you'll see that trend or that general topic coming out throughout the presentation. Before I get into the technical details, I just wanted to briefly mention our program at the Golisano Institute for Sustainability. It's an interdisciplinary graduate program with 3 degree offerings: a Master's of Science in Sustainable Systems, a Master of Architecture, and a PhD in Sustainability. And we have 3 primary research thrusts, and these include sustainable energy, circular economy, and sustainable urban systems. And I would also mention that the Institute houses the New York State Pollution Prevention Institute, which is entirely funded by the New York State Department of Environmental Conservation. The picture shown here is our Sustainability Institute Hall. This is an 88,000 square foot LEED Platinum certified building. It's entirely powered with the solar array you see on the top and a phosphoric acid fuel cell. So this building can be run entirely off grid. And so we're pretty proud of that facility. So to step back a minute and think about conventional waste management methods, what we've been doing in the US and really globally for well over a century is that waste materials, which generally have significant potential value, are treated by expending energy, and it's usually fossil energy, to render them quote unquote harmless. And the 2 primary pathways, of course, are landfilling and wastewater treatment plants. So the broader question we have in the context of sustainability is, how do we shift the paradigm from treating these materials as wastes, which we spend money and resources to discard, and turn those into resources which utilize and extract the inherent value. So these are some of the biomass waste utilization pathways that have been widely explored to date, and many of them have been studied by our research group here at RIT. After thinking about some of the logistical aspects of organic resource management and characterization, then one can start thinking about different potential valorization strategies. The most common ones are shown on the right-hand side, which would include things like animal feed and compost. But as we move to the left, there's other potentially higher value products that can be derived from agricultural waste. For example, we could generate, and this is being done on a wide scale now, bioplastics, specialty chemicals, fertilizers, nutraceuticals, and so forth. Probably the most expansive research and development activities, however, are in renewable energy. And here there's a lot of different options that have been explored. Methodologies including transesterification, anaerobic digestion, fermentation, gasification, pyrolysis, and hydrothermal liquefaction will generate a wide variety of biofuel types, including biodiesel, methane, ethanol, butanol, hydrogen, and bio-oil. And then from those products, we can derive transportation fuel, either on-site or grid electricity, power through fuel cells, and also boiler and space heatings. The focus of my talk today really focuses on the materials or the products in the lower left-hand corner. And these are what we would call byproducts that are separate from the primary energy products. Things like glycerol, which is a byproduct of the transesterification reaction, animal bedding, fertilizer, soil amendment, and the main focus of my talk today is biochar. So biochar is derived from thermochemical conversion, and we define that as heating at 400 to 800 degrees C in a reduced oxygen environment. And that process will generally produce 3 byproducts or co-products: hydrogen-rich syngas, a bio-oil, and the solid biochar fraction. When we talk about thermochemical conversion, the 2 main types that we consider are gasification, a process in which we're using less oxygen than the stoichiometric level needed for full combustion. And secondly, pyrolysis, which is a thermochemical conversion process in the complete absence of oxygen. So why is this process of interest? Well, some of the advantages are, number one, you can process material with a very short residence time. So that enables us to design systems that are physically smaller than, say, biochemical systems that require a much longer time for the microbial organisms to do their thing. The second advantage is resilience to feedstock variability. So although these processes can be designed for biomass conversion, we can process a lot of different things, including paper and plastics. Thermochemical conversion provides significant volume and mass reduction, carbon sequestration, and then biochar and the other co-products have many potential uses, which I'll touch on today. Of course, with any system, there's disadvantages to be considered as well. The main one for thermochemical conversion, at least gasification and pyrolysis, is that they may not be suitable for high moisture content wastes. The relative value of the co-products is not at this point very well understood from an economic sustainability standpoint. And one very important point that's really been a big barrier in the past is that policymakers often confuse these technologies with combustion and incineration. So that's something I know we've dealt with a lot in New York State and are continuing to deal with. So as I said, these systems provide short residence time, which makes their physical size suitable for deployment at even the scale of a single large waste generator. So say a large farm, a food processing plant, even a large grocery store or food distribution center. As I said, these technologies allow us to process mixed waste, biomass, paper, even plastic packaging. The output, biochar, is shelf stable for long term, and there's a significant mass reduction, up to 98%. And the schematic figure at the bottom illustrates this. For example, if we were to take 75 kilograms of raw food waste, and this is based on experiments we've run in our lab, we use a lab scale dehydrator to essentially remove the water, and that reduces that initial 75 kilograms to 15 kilograms of dried food waste. Then when we run it through our on-site pyrolysis system called the biogenic refinery, that system will generate a hydrogen-rich syngas and biochar at around a 10% yield. So we started with 75 kilograms and we end up with just 1.5 kilograms of solid product. So that's an important point from a logistical standpoint, where we don't want to spend a lot of resources and finances moving material from one site to another. The system that we have at RIT is the biomass control system manufactured in Woodstock, Connecticut. And this system would be considered a small commercial scale system that can process up to 1 ton of biomass waste per day. The biochar is produced, this actually should be 10 to 30% yield. And that material has a high carbon content, a high organic carbon content, and also a high surface area. And it's that high surface area and very significant surface porosity, which you can see in the lower right-hand corner, that gives biochar a lot of the unique properties and its ability to be used in several different applications, which I'll mention today. One application that I'd like to highlight is using biochar as an adsorbent for organic waste. This is maple wood-based biochar, which was used to extract the organic matter in tofu wastewater. And you can see the before and after scanning electron microscopy images there. That so-called enriched biochar was then used in greenhouse plant trials for lettuce and basil. And it was determined that whether we use filtered or unfiltered biochar, we had an enhancement in plant growth over the no biochar control. But in some cases, particularly for basil, the filtered biochar actually produced statistically significant greater plant growth than the biochar that was not used to filter the tofu wastewater. Another application is highlighted here, and this is really where our research is focusing on currently. This is an example of biochar bioplastic composites which use food and agricultural waste. In this case, we're using coffee grounds from the university cafeteria. We're again passing that through a dehydrator and then through our on-site pyrolysis system to generate coffee waste biochar. And then that material is blended at 10 weight% with a bioplastic called polylactic acid, and then thermoformed at 177 degrees C for 57 seconds. And through this process, we're able to produce a prototype of a black plastic coffee cup lid. So this is an example of the circular food economy that I know is central to this Congress and this webinar, where we're taking coffee waste and then generating a useful product back into the actual coffee cup production itself. So this is an example of the circular economy utilization of food and agriculture waste that is at the heart of our research. Another project that we're currently working on is biochar bioplastic composite agricultural mulch films. And this is a project that's funded by the Foundation for Food and Agriculture Research. So conventionally, agricultural mulch films at the end of the growing season are just collected and landfilled or incinerated. Of course, that has a lot of costs to society that are fairly obvious. In this project, we're taking common agricultural waste resources, including crop residues, woody biomass, pallets, and cardboard, and then again, creating the carbonaceous biochar, and then using that material with bioplastics to generate composite multi-layer agricultural mulch films, which can be shredded and tilled back into the soil at the end of the growing season. So not only will this process significantly accelerate the degradation of that agricultural mulch film, but it will return organic carbon to the soil for the next growing season. We're very interested in biochar from copyrolysis. So this is a process where we're considering mixtures of biomass, and in this case, plastic, low density polyethylene. So some recent experiments running 75 weight% woody biomass with 25% low density polyethylene produces biochar that's nearly identical to the biomass alone, biochar produced from the biomass alone. And as the results below show, with increasing fractions of low density polyethylene, there is some reduction in organic carbon content, as one would expect. However, the addition of low density polyethylene in the blend with the biomass actually helps generate secondary micropores that are illustrated in the center of the scanning electron microscope image. And that those secondary pores contribute extra surface area that actually enhance the absorptive capacity of these kinds of biochar materials. One focus of our research is the so-called biorefinery approach. And in this approach, we integrate multiple technologies to enhance the overall economic and environmental sustainability of the system. So we're particularly interested in combining anaerobic digestion and pyrolysis. So in this example, and this was done in collaboration with a local anaerobic digestion facility, this facility combines food waste and dairy manure in the anaerobic digester to produce biogas, of course, and generate electricity. But then there's a lot of concerns around how do we manage what comes out of the system, generally called digestate. In this system, we run that material through a screw press, separate it into solid and liquid fractions, pyrolyze the solid fraction to biochar, and then use that biochar to absorb the nutrients in the liquid phase. And what we found is that solid digestate produced at 1,000 degrees C has a very high phosphate absorption capacity with no secondary activation step, which is the case with activated carbon. So activated carbon that's produced from coal or coconut biomass or things of that nature usually has a rather expensive post pyrolysis activation step that increases the cost. So as shown in the upper figure here, the activated carbon clearly has significantly higher absorptive capacity than the biochar. But again, this biochar is produced with no secondary activation step. So the expectation is that this solid digestate biochar can be manufactured for much lower cost than the activated carbon and potentially provide an economic benefit despite the roughly 3x lower absorptive capacity. So this is really our end game that we like to think about, and my students are all kind of plugged into different parts of this diagram. But it's what we refer to as a community biorefinery. And the goal here is really to develop multiple co-products from multiple feedstocks. So we think with thermal chemical conversion technology, and here we would include pyrolysis and gasification, we can process a wide variety of feedstocks that are very common in any region, urban or rural. Food processing waste, dairy manure, institutional waste from university campuses, for example, all kinds of excess recyclables. There's lots and lots of cardboard that no one really knows what to do with nowadays, and things like lawn and tree residues. Some of those materials can go to anaerobic digesters, and that's becoming an increasingly common process. But even the digestate from the anaerobic digester and the biosolids from wastewater treatment, all of those materials can potentially be combined in a thermochemical conversion process to generate all of these different co-products. Syngas for electricity and heat, hydrogen for fuel cells, nitrogen, phosphorus, potassium fertilizers, biomaterials for the biochar itself, biofuels, bioplastics. And then we also should not forget about these ecosystem services: greenhouse gas emission mitigation, carbon sequestration, disposal fee avoidance, PFAS degradation in the food supply chain. This is becoming an increasingly challenging problem to deal with, but we believe thermochemical conversion can be part of the solution there. So all of those co-products and are viable and are in different phases of commercial development. But the key point here is that a wide variety of common feedstocks can be utilized and converted into useful products. So with that, I'll close and just mention that the research was supported by the National Science Foundation, the Foundation for Food and Agriculture Research, New York State Empire State Development, and also the New York State Department of Environmental Conservation. There's a very large number of students involved. Of course, they're the ones that actually are in the lab doing the work. That list is fairly large, so I did not include it. But I thank you for your time and your interest.
Thank you, Dr. Trabold, for your wonderful presentation. We heard many good examples with high potential of converting agricultural waste into products. So now there is one question in the Q&A session. The question says, in the coffee example of circular economy, how many times can the coffee cup be recycled through the processes? Is there a limit on how many times this circle can keep going?
Yeah, so that's a very good and relevant question. I don't have the answer to that. We have not tested that, but that's a question we often get. Right now, we're just at the point where we're evaluating the physical properties of that coffee waste biochar bioplastic composite and seeing if it actually would be suitable for that application. Of course, it has to be able to handle the high temperature, and you have to do a lot of toxicity testing and all that. So we have not gotten to the point yet where we figure out how many times we can recycle that.
Okay, great, thank you. I mean, in the following, let's have the second talk, and then at the end, hopefully we will have time for some discussion. So now let me introduce my colleague, Professor Zhang. Professor Zhang is a founder professor of agriculture and biological engineering here at the University of Illinois. He is an affiliated professor of mechanical science and engineering, as well as bioengineering. He's a registered professional engineer, a fellow of the American Society for Heating, Refrigeration, and Air Conditioning Engineers, and also a fellow of American Society of Agriculture and Biological Engineers. His research includes hydrothermal liquefaction, which is HTL, of bio-waste and algae into biocrot oil, upgrading HTL biocrot into transportation fuels, and valorizing post-HTL wastewater by recovery of nutrients and energy. Professor Zhang has published near 240 peer-reviewed journal papers, and he's author of a textbook, Indoor Air Quality Engineering. He teaches both undergraduate and graduate courses on building environment, HVAC systems, indoor air quality engineering, and research methodologies. I just want to emphasize Professor Zhang is a leader of one of our campus living labs based on his research work on bio-waste conversion. So the purpose of our living labs are to integrate research education with campus sustainability development. The good news is that Professor Zhang's living lab recently got some external funding from DOE. Yuanhui, now is your time.
So back to the general concept of circular economy in general, and keep the food and agricultural systems in particular. We from take, which is the production of the food, and make, and distribute, including transportation and end use, then dispose after the consumption. So in the entire circular economy scheme, these three links, recover, remake, and reuse, are really is our effort put in. And really the weak link is the recover, both from a technological and economical point of view. So keep those key components in the circular economy in mind. Really, this recovery is our weak link for the entire process. Our existing or current state of economy is pretty much in this shaded area. So we have a lot of room to expand. You can see from this diagram, if we can have some breakthrough both technologically and economically and maybe socially, social acceptance per se, the recovery, remake, and reuse. So the good news is since 2012, DOE have this milestone roadmaps about the biomass, converting the biomass into the bioenergy. By that time, 9 years ago, it's more focused on the grain-based or lignocellulose-based, which is ethanol. And bio-waste has not really in the radar screen. It's good news now. In 2017, DOE issued another roadmap. It's a biofuels and a byproduct from wet and gaseous waste streams, the challenges and opportunities. This really opened the door for the interest and effort and the resources into this wet waste stream treatment. This answered the two key questions. One, this is a turning point questions. Is bio-waste an impactful feedstock? Because DOE always only considers impactful feed waste. By definition, only those feedstocks produce 50 million ton per year. If less than that, they are not considered as impactful. And now we combine all those wet waste, including animal manure, the food waste, and the sludge. Combined together, it's way more than this 50 million ton per year threshold. The second question, is the hydrothermal liquefaction a bioenergy pathway? And also in this report is included. Before, whenever we talk about bioenergy, it's always anaerobic digestion or gasification or pyrolysis, but not include the hydrothermal liquefaction. So now that's to the research, my research. My research is being focused on the hydrothermal liquefaction. Thermal liquefaction, first, known as the Fischer-Tropsch synthesis, can be dated back to 1920s. Germany liquefied coal to heavy oils for military use during the World War II. And still, South Africa hosted one of the largest coal thermal liquefaction, CTL facility in the world. Now, what's the hydrothermal liquefaction different from that is to thermally liquefies, including the water. So that is good for wet organic waste. So at this moment, there are a few research institutes or key players working on this, especially at the working towards the pilot scale, including Pacific Northwest National Lab and University of Illinois. Here is my group, and in Denmark, Aalborg universities, and in Australia, University of Adelaide. And they are starting some commercial level of a trial. That's Metro Vancouver Sanitary District and collaborated with the Genefuel. They are trying some pilot scale hydrothermal liquefaction using the municipality sludge. So this is the kind of a current state of this hydrothermal liquefaction research. So now let's give a quick overview of my group's approach. So we take this EE fuels paradigm. It's environmentally enhancing food, energy, and water systems. We're starting with the bio waste, and including food waste, animal waste, sludge, and algal blooms. Then we separate into the solid and doing the hydrothermal liquefaction, and the liquid parts, which contain most of the nutrient, nitrogen, phosphorus, etc. And we can pre-treat it or even growing algae and treat the wastewater. And then the algal biomass can feed back into the hydrothermal liquefaction and forming up this kind of multi-cycle recirculations. This whole paradigm serves as a biomass amplifier. And this HTL process produces the biocrude oil, which is similar to our petroleum. And this process also mimics the Mother Nature's process for our petroleum, is the biomass buried underneath the ground through million years of high temperature and high pressure processes that's what we get today's all those petroleum. By the biogenic theories, all our oils is come from algae and coal from wood and peats. That's kind of a biomass. So during the process, we can also utilize or recover and utilize nutrients in this original bio waste to grow food. And of course, this whole process, after we extract the carbon and the nutrient, then we clean the water. So that is our technical kind of route maps for our environmental enhancing food, energy, and water systems. So recently, this work, after the 2017 DOE's new roadmap, we obtained 2 DOE projects specifically treating the organic waste. My group also obtained the funding from Army to deal with the algal blooms in the country, in New York and Wisconsin and Florida area. So we tried different type of wet organic waste, including food processing waste from a food processing plant, slaughterhouses, and swine manure, and also municipality wastewater algal biomass. So give you a quick overview of this result. We have a pretty good oil yield. These are all based on the dry and ash-free biomass. 62% oil conversion for food processing, 72% for slaughter. That's not surprising because it's containing lots of fat. And for swine manure, it's also pretty good. It's because it contains a good amount of the lipid and proteins. Even for the municipality wastewater algae, we get anywhere from 30 to 46% of the oil conversions. So this technology shows that the promises can be effectively convert those kind of wet bio waste into this bio crude oils. So my group's research is focused on how to improve the HTO conversion efficiencies. We focus on the severity factors. The severity factor means temperature, pressure, retention time, etc. Those are combined all together. We have we call this reaction severity factors. So this is one of the major research objectives to determine the optimized reaction conditions, so we can get different fractions of the product, bio-crude oil, and the solid residues, and aqueous stream and the gases. So our goal, of course, is to get as much of the carbon and the hydrogen into the fuel streams, and get all those nutrients into the aqueous so we can recover and reuse it. So that is one of the research emphasis. We also looked into different approaches for this hydrothermal liquefaction, including some combining biological, chemical, and thermal approaches. In this particular project, we tried the so-called dark fermentation hydrothermal liquefaction. So we first do some biological treatment through the anaerobic digestion, produce some hydrogens, and then do the hydrothermal. And later on, those hydrogen, we hope, we are still in the research stage, we can use this hydrogen for hydrogenating or hydrogen treating our bio-crude oil to upgrade those bio-crude into transportation grade fuels. So that is one of those research approaches. And from here, just to look at the energy pathway. The energy in the traditional or the conventional HTL, we have the 80% of the energy into the oil. But through this different approach, dark fermentation, we can get 66%, 2/3% of the energy and into the oil streams. The rest would be increases more like we also look at the nitrogen pathways. Okay, and again, we want to also focus on recovery the nutrient and reuse it for other applications, such as the grow the vegetables or produce algal biomass. So you can see the differences with the different approaches. We can improve the energy recovery, and also energy recovery is directly related to the carbon recovery, and also the nutrient recovery, which is the nitrogens. Those are all we look at. We basically look at the carbon and energy recovery, because those are the primary concerns from DOE's point of view. So through the years, right now, my group developed this pilot reactors, and we call them mobile. And right now we are using this, and the US Army, actually, we have the contract with them to treat the algal blooms in the lakes in United States. And so this unit allowed us, give us some capability for research, is to produce up 1 ton of the feedstocks, and this is right here. That's the crude oil. This is the continuous process. So we can produce 100 liters of crude oil right now. This is it's right from this. This is our product output. So this is on campus, and based on our capacities, and recently DOE have funded my group 2 projects. One is for the food waste conversion, the other is for algal conversions. So with these capacities, that allows us to looking further down the road. How can we upgrading this biocrude oil into transportation fuels, that's including the diesel and jet fuels? So we are focused on the this simple Venn traveling diagrams. So we are focused on converting our biocrude oil right here. That's through the upgrading, especially catalysis upgrading to denitrogenation and the deoxygenation processes, so we can get the higher quality, either the kerosene or the diesel. Okay, so those are our another emphasis right now, our research. So our ultimate goal is, if we can produce sufficient amounts of biocrude oil, and our industry already very well developed with upgrading. However, this is the new stuff, and the upgrading part, hydrogenation or catalysis treatment, is going to be different. So my lab has been successfully at the lab skills, got the diesel grade, and now we are working on the jet fuel grade oils. Because we have enough of the biocrude oil, we can play around with that. This is a major step move from lab scale to pilot scale, because in the lab scale, we cannot do this kind of things because we don't have enough of biocrude oil to treat with. Here is a kind of end game, or the more picturistic diagrams. The environment enhancing EE-fuse approach can be applied to both a rural setting, we call the rural EE-fuse. See, with all kinds of waste, animal waste or food waste, first we through the hydrothermal liquefaction, nutrient can be recycled for agricultural production, and also can be used for algal culture. And then after that, upgrading then can be end up with useful or consumption and fuels, diesel or jet fuels. And during this whole process, we clean the water from the waste, and then we can discharge that back to our environment. That's the rural setting. And in the urban settings, similarly, we can take off the activated sludge from wastewater, and also the food waste from the dining halls, restaurant, and doing the similar things, hydrothermal liquefaction first, upgrading, and then the remaining for the agricultural or the algal productions. At the end product, the fuel will be for our transportation fuels. So that is kind of our overall end games. In this entire systems, though, we focus on the recovery and the reuse, both from energy point of view and also the nutrient, carbon and nitrogen point of view. So with that, I just give you a quick overview. I would thank our funding agencies. As I mentioned, the current job research is funded by US DOE and US Army and also National Science Foundation. And more importantly, I want to thank my group, my graduate students. They are the working horses on the project. With that, thank you for your attention, and I'm ready for questions. Okay, I have one question. The question here, how does the pollution from thermochemical conversion compare to pollution from combustion? Well, because we consider our processes nearly zero emissions in terms of pollution is measured by the carbon emission. Now, after we got the crude oil, you end up with the transportation because our feedstock, all those carbon is comes from the bio source, food or algal, anything of this is through the photosynthetic. All the carbons from the plant absorbing the carbon dioxide from atmosphere. So in that regards, our biofuels can be considered as a renewable fuel. Instead of dig out from the petroleum is our carbon stored underneath the earth. So and our biofuels is produced. It's all can be traced back to the photosynthetic bio-based. So in that regards, our carbon emission can be considered renewable and zero emissions. Of course, then during the process, we will need to use other energies like electricity or heat. But if those energy, that's involved the overall energy efficiency. I would say our systems, the HTL systems, we already figured out, and through our tests, our pilots already can achieve 90% of energy efficiency, which means 10 part of the energy produced only need less than 10% used for those processes. So it's very promising, much higher than the traditional anaerobic digestion or pyrolysis. So that's the first from Margaret. Margaret question.
Yeah, thank you, Yuanhui. Thank you for your answer for the question. Let's move to the next question. What is the shelf life of the bio-crude oil, and have we characterized the components of bio-oil? Yuanhui or Thomas, if you have any comments on this question.
Yes, this is a really good question. And the shelf life, because this whole research has been short, if we are still continue work on it, is one of the topics we are actually, one of my students is publishing a paper now on that. We study the shelf life and also the time effect on the stability of the chemical component. So we are, every batch we run, we characterize that, both for bio-crude oil and upgraded refined oil. So it's an ongoing research, and it's a major part of the research is to characterize the crude oil and the upgraded oil.
Okay. Thomas, do you have any additional comments on either of these questions discussed about?
Well, I think those are really directed toward the Professor Zhang's hydrothermal liquefaction research and the bio oil, and the research we do on pyrolysis and gasification. The focus is on the solid carbon fraction and less on the bio oil or the syngas phase. So the system, as I think I mentioned early on, and it was clear in Professor Zhang's presentation, hydrothermal liquefaction is very well suited for wet waste. We tend to look more at dry waste, which would, there's some advantages to that with more conventional pyrolysis or gasification, where the interest is in using biochar for some of the products I mentioned, but also for carbon sequestration, because that biochar can store that carbon for a long term.
Okay. I just have a general question for both panelists.
Mm-hmm.
People recognize the value of circular economy with large potential for sustainability, but people also have some concerns about the environmental or public health impact. So possibly some unintended impacts. Can both of you comment on that? Thanks.
Sure, Professor Zhang, why don't you go ahead and then I'll.
Sure. Actually, there are two additional dimensions. One is the environmental concern, and the two is the human health concern. And also there was an economical concern, of course. There were the four dimensions we think about is the technical, economical, environmental, and health concerns. So those are the four major dimensions. And if we made from renewable materials from a very beginning, we are in a good ground. Mm-hmm. Because all the materials we are trying to recover is from natural resources. Of course, during the process, we might create some unexpected chemicals or compound, but that is, again, we cannot answer 100%. It's a part of the research and part of our whole society's development. So, but on the other hand, we are a circular economy. We're sitting on a firm ground. It's naturally, it makes more sense. Then we dig out the petroleum and turn into these things into CO2 again, or we use the natural chemical and combine all those chemicals, formula something are good examples of those pesticide and the herbicide. All those things are really concern for the both environmental and health concern. Then if we recover from neutral or nature resources, this concern immediately. Well, I kind of claim that if I convert something from manure, people will like it. But on the other hand, if you think deep, manure is come from food originally. Mm-hmm. So if we do it right, it's still within this natural cycle.
Some psychological issues.
Yeah.
Thomas, do you have? Thank you, Yuanhui. Thomas, can you add to that?
Yeah, and I agree with everything that Professor Zhang mentioned. The only thing I would add is, education is a huge part of this, not just the education in the university environment, but educating in the public sphere, right? I know in the technologies we work on, they're often confused with conventional incineration plants, and those have a bad reputation and a checkered history because many of those incineration plants were located in underserved communities, low-income communities, and the health impacts were really disproportionately felt by those communities. So I know in New York State we have to do a lot of work to go to the public forums and talk about these things and educate people on why these technologies are different than the conventional technologies and why they're better from the standpoint of not only environmental sustainability, but human health. And I think we can make a clear case, but we as researchers got to get outside of the university environment and be able to communicate those things to different stakeholders.
Totally agree, Tom. This education is really a key component. That's our iSEE is doing, right? Louis is charging on this education part.
Yeah, that's great. I mean, that's at the heart of our Institute for Sustainability. I think we're all speaking the same language. It really has to be community education to make these things a reality.
Yeah, that's just a wonderful point. Thank you both. I think it's almost the time. Finally, I would let our interim director, Madokana or Luis Rodriguez, one of you can make a conclusion remark.
Thanks, Ximing, and thanks, Yuanhui, and thanks, Thomas, for some very interesting talks. And thanks, Tony and his team for running the behind the scenes for a smooth and effective Congress. Thank you all for attending and for the great questions. This year, this is our concluding presentation for the Congress this fall. But I'll emphasize the questions, the educational opportunities that so nicely were wrapped into the end of our conversation there are an ongoing process that we hope to keep sustainable in and of itself and present at all times. So be looking for future opportunities for us to continue these conversations on into the future. We'll be looking for advertising opportunities for us together into the spring on topics such as regenerative agriculture. We'll keep all these Congress registrants posted with any new developments. So thank you for your participation. And of course, we hope next fall that we'll be back again, and hopefully even in person if the pandemic can continue to improve and cooperate with us. In the meantime, if you missed any of the webinars for this Congress, some of them are posted already, and they'll be up, and if not, they'll be posted soon to our website at sustainability.illinois.edu. We hope you have all a good afternoon, and I'll thank you all once again for participating.